Hi everyone, and welcome to the lecture on the ozone hole. And it's a very interesting situation, the ozone hole. It was almost an Armageddon situation where life as we know it on our Earth would not have been the same if we had continued to deplete the ozone layer. So let's go ahead and get into the topic and see how we were actually, as a community, as a global community, able to resolve this worldwide dilemma. So ozone depletion in the stratosphere was first identified in 1982 in Antarctica. You can actually see the hole here in this image. So the blue just indicates that there's very low to no levels of ozone. So this is the entire hole here. What was discovered, actually even before that, in 1974, Rowland, he's a famous scientist, identified that CFCs could cause an ozone hole. And later him and Molina earned the Nobel Prize for their work on discovering how CFCs cause the hole. He's a big hero at UC Irvine, where I went to graduate school. He used to work at UC Irvine before he passed away a while ago. And we actually named our chemistry building, one of our chemistry buildings, after him. We named it Rowland. So he's one of our local heroes. And basically, what was discovered is that these CFCs, which are chlorofluorocarbons, so you have chlorine, fluorine, carbon, such as Freon is one of the ones you might have heard of, break down ozone in the stratosphere. And you would find these products, these CFCs, in air conditioners, refrigerators, like spray cans, cleaners for electric parts, sterilizing medical instruments, fumigants, and many other places. And actually, originally, CFCs were kind of seen as a wonderful new chemical when it first came out on the market in the earlier part of the 20th century. They were highly stable. So, for example, refrigerators used to use sulfur dioxide, methyl chloride, and ammonia to keep the food cold. And these could be explosive or poisonous if they were actually to leak out. So it was a little scary. And when CFCs were discovered, it was like, wow, these are inert. They don't react with anything. That was the problem. They didn't react. So they were so unreactive, they would actually get all the way up into the stratosphere. They'd go past the entire troposphere and never break down. And finally, when they got to the stratosphere, that is when they started causing all the problems. Basically, what happens with CFCs, so here's an example. Once you have carbon, you have fluorine, and 3 chlorines on this guy. Here's another example of a different type. This is Freon 12, that one's Freon 11. This one is carbon with 2 chlorines and 2 fluorides. The first step is the UV radiation. You have a photon of less than 220 nanometers. It will it interacts with your Freon or your CFC, and it'll break the carbon-halogen bond. So in this example, it broke the bond, well, it would be this molecule. It broke the bond on the chlorine and the carbon. So you're left with a free radical chlorine floating around in space, or the stratosphere. The free radical chlorine, here you go, right there, can then react with the ozone and produce 2 ClO plus 2 oxygen. So then the 2, this is also called chlorine monoxide radicals, because notice the dot here, it's a radical. Those can combine together, they can react to each other. Okay, and then you get this new molecule, which then can react with more UV light to give you ClO radical plus chlorine radical. And that would actually break down into chlorine radical again plus oxygen. And that chlorine radical is special, right? What can that chlorine radical go do? It can go back to the first step here and react with ozone again. And you repeat the whole process over. So one chlorine atom, they say, for each CFC molecule can destroy 100,000 ozone molecules over decades, because it keeps getting, the chlorine radical gets consumed in the reaction and then gets generated again. And that's what we call a catalyst. So chlorine actually is a catalyst. You can see that it actually in the end is not used up. It goes in and comes out, goes in, comes out. So it catalyzes, it makes the reaction occur faster. And so your net reaction here is for 2 ozone molecules, you would produce 3 oxygen molecules. This is your net reaction, because everything else cancels out. The chlorine radicals cancel out, your ClO, your chlorine monoxide radicals cancel out. Everything cancels out, but in the end you're left with this net result of a loss of ozone and a gain of oxygen. Experimental analysis have shown that the chlorine oxide radical concentrations increase as ozone concentration decreases. So here's your stratospheric ozone, right? The y-axis is parts per billion, we already went over that, and your x-axis is degrees in south latitude. So notice that the stratospheric ozone is slowly going down here to a lower level. And at the same time, your stratospheric chlorine is going up. Here's a really striking, these are really striking images for me. If you look at, these are all taken by NASA, satellite images measuring the ozone. And you can look at this first measurement here in 1979. Already you can start seeing a hole forming. And again, the CFCs are recent in our history. And so, but already at this time, you're starting to see a hole forming. And 10 years later, you have a significantly large hole. In 2006, it gets bigger. 2010, it gets bigger. And 2013 is a special year. I'll get into that in just a minute. But the one thing to take into consideration is, why is this hole localized so much in the southern region of our planet? You do see loss of ozone throughout the entire planet, but the main loss is here in the Antarctic. And I'll talk about that with you in the next slide. The thing that's so special about the 2013 year, that's why it's like black around it, is because this is the first year that it was identified that the ozone hole stabilized. It hadn't repaired, but it had stabilized. It was the first year since 1979 that the ozone hole did not grow bigger. So something changed. We made a global movement and banned CFCs, and this is finally showing results here in this 2013. And obviously now that it's been years since then, you would expect the results to be getting better and better. The reason why you see the ozone depletion in Antarctica, mostly there, is because it has special conditions. One, it has very cold winters. And you can just see that based on the Earth's orbit, that it's, in this part of the world, it's dark. In its winter time, it's dark all day, all night. And so the warmer air is isolated. It's not in this region. And what you end up getting is these clouds of ice in the stratosphere that form in the winter. And the CFCs actually attach to the ice, and they end up getting concentrated over the winter. And then when the sunlight returns to the polar region in the spring, all those CFCs that have been concentrated on the ice get released, and then they start eating up the ozone. So why do we even care about the ozone, right? It can have the thinning of the ozone can have severe consequences on life. And this depends primarily on the energy associated with the radiation. So we're talking about UVA, UVB, UVC, and the length of time of your exposure, or of the exposure, and the sensitivity of the organism to that radiation. Some organisms can handle it better than others. What we find is that with the thinning of the ozone layer, we've had more sunburns. The sun can damage the skin cells, more damage to the eyes, and just to get you an idea, eye cataracts are significant. It's caused a lot from the sun, and it dims or blinds people, and there's about 30 million people worldwide who have this condition. UV light damages DNA. It's also immune system suppressant. It increases in acid deposition, which is bad for the soil, for the ocean, and it kills phytoplankton. These are important for the ocean. Those are basically that's the beginning of the food chain in the ocean. So that can impact life greatly. And it can also damage crops. And one thing I want you to consider is, how does thinning ozone layer impact photochemical smog? Right? Does it increase the temperatures or the sunlight? Can that increase photochemical smog? And the other one you should consider is, how can it impact global warming? NASA, in one of its studies, identified that for every 1% decrease in the ozone concentration, there will be a 2% increase in UV radiation, causing a 4 to 6% increase in skin cancers. And this is already seen from this report, in this graph in a report from the World Health Organization. If you look at the y-axis, this is excess cases of skin cancer per million per year, so this is more than what's normal. And on the x-axis are the years. So you can see in 2000 there's an excess, and without restrictions on CFCs, you would have seen a significant excess. With the original restrictions set in place, there would still be, an exponential increase in skin cancers. However, with the Copenhagen Amendment, you actually can see there will be a peak of excess approximately in 2050, and then a decline of skin cancers back to baseline here when the ozone hole heals itself. That graph actually is very similar to the graph about ozone abundance. So here's abundance, and here are the years. The green line indicates no protocol, nothing happened. We just went business as usual with CFCs and continued to destroy our world. And in 1987, we had a global community came together, and 57 countries signed to reduce CFCs by 50% by 1998 and start using an alternative type of chemical called HCFCs, which are, by the way, a greenhouse gas. But you can see that Montreal Protocol was not sufficient. We would still see, again, an exponential increase in CFCs. In 1992, we had the Copenhagen Protocol, but that's the big one. And that's where we had 177 countries signed to phase out all CFCs by 1996. And it also helped fund poor countries to transition away from CFCs. And this is an important example of what we can do as a global community and what we will need to do in order to combat global warming. We will need to do something. HCFCs are one of the alternatives to CFCs. They decompose more readily in the troposphere, so they're not as inert, and they will not accumulate to the same extent in the stratosphere. So, for example, you can see here, the main difference between CFCs is this hydrogen. That's why they're called HCFCs. So you have hydrogen, and then you have the fluorines and chlorines. So question for you. Why will the full recovery of the ozone not take place until approximately 2050? These CFCs take about 10 to 20 years to actually get into the stratosphere. And then the CFCs take another additional 65 to 385 years to break down. So it's quite a long time. All right, well, I hope you enjoyed that lecture on CFCs and the ozone hole. Now you can share the story with your friends and family. Okay, I will see you next time. Bye.